Hi, my name is Annie, and I'm part of the Clements Rangers, and this is our CubeSat design review. Meet the team. This Christine is on the left, Amaris is in the middle, and I'm on the right. And of course, we have Marcellus the cactus. Our concept of operation starts with the satellite power off. We test, and if it succeeds, we launch. Then we see if it's in orbit. If that succeeds, our camera comes on, and if not, we have built-in software to fix issues. Assuming that the camera is on, we take a picture, and then we send that picture to the ground in order to detect the colorful plastic. Should it not succeed in any step, then it will first fall into the built-in software to fix the issue. And if that gets fixed, it'll move on to the next step. If not, it will move to failure.
All right, next we have our system level block diagram. And so you can see that we separated our systems into 6 different subsystems. And the Raspberry Pi is kind of in the middle of all of this, and it's connected to a bunch of different things like the imaging and the communication, the attitude determination subsystems, as well as the power, which is connected back into our more physical subsystem, which is the structure subsystem. And that consists of our solar panels, which provide the energy for our CubeSat, as well as the overall chassis. Yeah.
This is a mechanical drawing of our CubeSat. Our central component, the Raspberry Pi, is represented by the green rectangle. We plan to place it in the bottom corner and suspend it on a few stands, which are the cylinders in the diagram. The Raspberry Pi is connected to the camera, the light blue square on the right face of the CubeSat. We have strategically placed the camera here so that it will match the square holes in the acrylic panels when we assemble the structure. To power our Raspberry Pi and camera, we included a solar panel, the dark blue square on the top face of the CubeSat. To ensure that our CubeSat stays functional during periods of reduced or no sunlight, we included a battery pack in the remaining space inside the CubeSat, represented by the black box. We have a total of 3 components for our power budget: the Raspberry Pi, the IMU, and the camera. We can only find accurate values for all the categories for our Raspberry Pi. With a peak power of 5.5 watts and a contingency of 20%, we expected to use a maximum of 6.6 watts. For the other 2 components, the peak power is only an approximation, but it is undoubtedly much less than the Raspberry Pi. Using 20% contingency again, we expect the power usage to be 0.012 watts and 0.64 watts for the IMU and camera respectively. In total, this gives us a total power usage of 7.252 watts.
Here's our mass and material budget. We have all the materials and equipment on the left with the Raspberry Pi, the SD card, the camera and case, IMU, battery pack, solar panel, USB cable, acrylic panels, side rails, screws, nylon standoffs, hex nuts, brackets, and female to female jumper wires. The mass is measured in kilograms and the cost is in dollars. All the costs have been rounded up to the nearest dollar, or in the female to female jumpers to 50 cents, just so that we have some wiggle room when it comes to estimating. Our total mass came out to be 553.8 grams, or 0.5538 kilograms. And our total cost came out to be $183.50.
Now for the data budget, we're going to be using 640 by 480 JPEGs, and it's going to be at 20 bits per pixel. And so the JPEG format is going to allow us to minimize our image size while still retaining some quality. And so the data will be sent from the CubeSat to the ground station, and it's going to mainly consist of the images that it takes and text files that contains like the date and the location that it took the image. And then the average bytes per image is about 200 kilobytes, and the average bytes per text file is going to be 30 bytes. So with an estimated rate of around 20 kilobytes per second for transmission of data, it would take approximately 10 seconds per image to downlink it to our ground station.
Our software architecture starts with the picture being taken and sent to ground. We then negate all the background color, which would be the ocean in this case. If we see that most of the picture is negated, which would be a threshold that is predetermined, then we delete the picture. If there are other noticeable pixels, then we will use it to distinguish between trash and other objects through a certain algorithm. If these pixels are ruled to be trash, then we will catalog its location, time, and rough size of the trash. If not, and we see that the pixels are ruled to be not trash, such as glare, other objects like boats or islands, then we will also delete this picture.
All right, and then we have our integration and our test plan. So first we have our structure integration and then our electrical harness integration. And then we have our power integration and testing, which we're gonna substitute as INT. And then so we have our electronics INT, battery installation, thermal component integration, avionics INT, flight software testing, ADCS, INT, comms INT, solar panel INT, camera INT, and then we're going to have to test for the electromagnetic interference. So that's the EMI or EMC testing. And then we're going to check that our comms and our radio frequency are going to be compatible. And then we have our vibration test, acoustics test, and thermal test. And after all of these different tests, we're going to kind of put it all together, make sure that it's all working and ready to go for launch. This was our Clements Rangers CubeSat design review video. Thank you guys for watching.